All right. Welcome to this screencast. It's from the Chemistry in the Community, section 2.C.5, and it's on collision theory. The objective from my class was to explain the effect of a catalyst on a reaction using collision theory. So going back to the kinetic molecular theory, one of the postulates says that molecules in a gas collide with each other and the container. And this is actually where we get the idea of pressure from. So the force of those collisions with the outside of the container is what creates pressure. In an ideal gas, and remember, an ideal gas is not necessarily the real gases that we experience in our everyday life around us, but in an ideal gas, the molecules will bounce off of each other with no loss of energy. But in the real world, we see something a little bit different. So could it always be true that every time air molecules collide, they don't lose any energy? Hopefully you're thinking back to the grand idea that in every collision, there is a loss of energy. And that's true for real gases as well. So you can do experiments to show this. You can make observations. Sometimes when particles collide, they do in fact create new molecules. Here's an example. Methane and oxygen burns. It creates water and carbon dioxide. In class, we had our discussion about the landfill and how the microbes that break down the material in the landfill actually produce methane as a side effect or as a byproduct. This methane would build up in the landfill. So pipes are put into at various points in the landfill so that the methane has a way to be released. Oftentimes, landfills will then burn this methane. It creates carbon dioxide and water. Now, the methane and the oxygen, they have to collide at just the right angle to break these bonds, because if you'll notice in this picture, the atoms get rearranged into the carbon dioxide and water. So the oxygen and methane molecules have to collide at just the right angle to break those bonds, but they also have to have a certain amount of energy in that collision. Think about a car crash. If you have a little fender bender where you bump into someone in the parking lot, the force of the impact is not as great. So you may just dent their bumper a little bit. However, if you're moving faster and you clip their bumper, you may rip the bumper off. So speed and the kinetic energy involved in their movement has an effect on whether or not these molecules are going to come apart. Once they come apart, they are going to rearrange and form new substances. So, in a nutshell, the collision theory, reactions can occur only if the molecules collide with sufficient energy, and in this case, they get a lot of that energy from the speed at which they are moving. They also have to collide at the correct angle to disrupt those bonds and for new ones to be made. The energy that's required for those bonds to be broken or to start the reaction is called activation energy. Most of you, if you're in chemistry, you took biology before this, and perhaps you're thinking back to where you have seen a similar graph in biology. All of the chemical reactions that happen in your body require a certain amount of activation energy as well. So how do we overcome this activation energy? Because oftentimes this is way more than we have the ability to overcome. Going back to the atmosphere, at standard temperature and pressure, it's pretty rare that collisions happen at the right angle and with enough speed to create new molecules. On the whole, this is a pretty good thing for humans, because if our oxygen were constantly being bombarded and broken down and rearranged into water vapor or other things, we might be in trouble. So it's actually a good thing that our atmosphere is somewhat stable. So why are these reactions fairly rare in our atmosphere? And again, what are the chances that the molecules are going to hit at just the right angle and have the right amount of speed or energy to break and reform bonds? And at standard temperature and pressure, it just doesn't happen very often. So because it doesn't happen very often, you have to have a catalyst. And a catalyst is any substance that lowers the activation energy needed for a chemical reaction. A throwback to the biology that you studied, there was a specific kind of protein called an enzyme, and you have lots of different kinds of enzymes in your body, and each of those enzymes lower the activation energy for the different chemical reactions that go on. The best example is in digestion. When you eat food, what are the chances that the food in your stomach is going to naturally break those bonds and reform into something else? And the answer to that is probably not fast enough for your cells. So you have enzymes that help you digest your food. Enzymes help you do all sorts of things, and they're catalysts that happen in a living organism. Now, outside of a living organism, catalysts can be all sorts of things. They can be elements and compounds. Inside organisms, catalysts are often proteins called enzymes. Hopefully you have seen this graph before in biology in your discussion of enzymes. But without a catalyst, the reactants here's your energy, would need this amount of energy. So they would have to have the correct position and hit each other in the right way. But not only do they have to hit each other in the right way, they have to reach this amount of energy from their kinetic movement, from their speed. If you have a catalyst involved, it positions the molecules in just the right way, increasing the chances that those two molecules will collide at the right angle. The catalyst may also lower the activation energy by doing several things, as far as weakening the bonds, changing the shape of the molecule. There are lots of things that it can do. An example from your book: in the 70s, we started to pay attention to our atmosphere and the pollution in it, and the Environmental Protection Agency passed the Clean Air Act in 1970. This was the first sort of government regulation that limited car emissions, so this is when the whole idea of emissions testing started. Manufacturers had to come up with a way for the gases emitted from the engine, the combustion engine, so the burning of the gases and the fuel, how to turn those emissions into something less harmful. And the invention that came out of that is the catalytic converter. Now, up here in the corner, this is what the catalytic converter looks like whole. If you were to split it open, you see that it has several chambers, and the gas goes in one side as harmful gases and comes out the other side as less harmful gases. And if you follow along the next set of notes, we'll actually take a look at those equations and do some things with them. So there's a video here, and jot down some things, 2 things a reaction must have. You may already know those because we've discussed them. And then there are actually 5 ways to speed up a reaction. If you can pull out 2 from the video, that would be great.
Meet our chemist, Harriet. She has a chemical reaction reaction that needs to occur more quickly. Our chemist has some processes at her disposal that can help her speed up her reaction, and she knows of 5 ways. And to remember them, she thinks back to her days as a high school student, and the day she got a date for the dance. Harriet was in high school studying between classes. She had lost track of time and was going to be late to class. Unbeknownst to her, Harold, who was just around the corner, was running late too. They both sprinted to class, and as it happened, sprinted directly into one another. Now, this was no small collision. They ran squarely into one another in such a way that he knocked the books right out of her hand. "I'm sorry," he said. "Let me help you with your books." He kindly helped her recollect her belongings and politely offered to walk her to class. And you'll never guess who went together to the dance later that year. Yep, those two. So as we can see from this example, the key to getting a date for the dance is to collide with someone and knock the books out of their hands. Now, you're probably already aware that not all collisions lead to dates for the dance, thankfully. The collisions must have 2 important characteristics. 1, correct orientation that allows books to be knocked from one's hands, and 2, enough energy to knock the books out. Shortly after this incident, Harriet decided to tell me, her chemistry teacher, all about it. I noticed some interesting parallels between her story and chemical reaction rates, which happened to be what she was studying in the hallway the day of the collision. Together, we decided to set out on 2 missions. Harriet wanted to help all chemistry students and chemists remember how to speed up the rate of chemical reactions, and I, being the nice guy that I am, decided to make it my mission to help create educational environments in which more book-dropping collisions can take place to increase future chemists' chances of getting a date for the dance. In order to facilitate this improved dance date-getting process, I propose 5 changes to all schools that parallel Harriet's 5 ways to increase chemical reaction rates. First, I propose that we shrink the size of the hallways. This will make it more difficult to safely navigate the hallways and will cause more collisions than in larger hallways. And by increasing the number of collisions, we increase the likelihood that some of those collisions will have the correct alignment and enough energy to create a date to the dance. Now, chemically speaking, this is equivalent to lowering the volume of a reaction vessel or a reaction mixture. In doing so, the individual particles are closer together and more collisions will occur. More collisions means a greater likelihood that collisions with the appropriate energy and configuration will happen. Second, I propose increasing the overall population of the school. More students equals more collisions. By increasing the number of particles available for collision, we create an environment where more collisions can take place. Third, we must reduce the time allowed between classes. Heck, let's just cut it in half. In doing so, students will need to move more quickly to get from one class to the next. This increase in velocity will help make sure collisions have the appropriate amount of energy necessary to ensure book dropping. This is analogous to increasing the temperature of the reaction mixture. Higher temperature means particles are moving faster. Faster moving particles means more energy and a greater likelihood of reaction causing collision. Fourth, students must stop traveling in packs. By traveling in packs, those students on the outside of the pack insulate those in the middle from undergoing any collisions. By splitting up, each student has some more area exposed that is available for a collision from a passing student. When particles travel in packs, the surface area is very small, and only the outside particles can collide. However, by breaking up the clumps into individual particles, the total surface area is increased, and each particle has an exposed surface that can react. Fifth, and finally, we hire a matchmaker. Is this colliding and book dropping too violent? Is there an easier way to get a date that requires less initial energy? Then a matchmaker will help with this. The matchmaker makes it easier for a couple to get together by coordinating the match. Our matchmaker is like a catalyst. Chemical catalysts function by lowering the activation energy. In other words, by lowering the energy required to start a reaction. They do this by bringing 2 particles together and orienting them correctly in space so that the 2 can meet at the correct configuration and allow a reaction to take place. So, to sum up, if a future chemist wants a date for the dance, he must collide with another person and knock the books out of their hands. And if a chemist wants to make a chemical reaction occur, the particles must collide in the correct orientation with an appropriate amount of energy. And both of these processes can be accelerated using the 5 methods I've described.
So as you can see, the video made it clear that the 2 things that a reaction must have are enough energy and the proper orientation. One way to reduce the energy needed is with a catalyst. So that was the finishing up the notes, and that's it.